All right. So how'd that exam go this morning? Don't want to talk about it?
There was one problem that was just, we decided not to even study it because it was so big compared to the other ones, and then it was 20% of the test.
I was gonna say that it's because it's so big compared to the others. Like that sounds like it's so complex. Okay. I was gonna say that sounds a little backwards.
And we were like, no way is you put this huge problem on there. You only have 7 in an hour and a half. I'm a gibberish and
Oh, no.
was so tough. Yeah. It was like the height here is 30. The thing we need to solve was this tall. I had 29 for that. And I was like, this is less than the short part. I was like, I can't do this. I can't find the pictures.
Well, the good thing is it sounds like you're all in the same boat, right?
So you're
Right.
That's
the hope. Right.
He made his speech that he doesn't curve, so don't bother asking him. No, he curves. And then what we see in Google is curve. So if we want that to be bumped additionally, he's like, no, I already heard this again. You know?
Right.
I don't know. That was mean.
Well, good luck with that.
We'll graduate.
Yeah. It'll happen, right? Okay, so today we're going to kind of pick back up. We had been talking about latrines and composting, what to do with the waste. Today we're going to talk about septic systems, how those could be applied, what those might look like. We saw a few photos from the big bulk I showed you earlier, and I might come back to a couple of those, see if I can find specifics, or I might have to do that next time. Get some specific pits they were digging last year. I don't have those photos quite on hand, I don't think. But today we'll talk about, okay, if we have enough water to justify like the fact that we need to deal with more than just mostly solids, then what do we do, right? Because we might have a situation where we could have a system that has some sort of a seep pit where you have the septic pit. And I mean, this would actually be typical for a standard pit latrine is the liquids will seep into the surrounding soil. That's kind of by design, so you don't fill it up with liquids, right? You don't want a sealed container and then nowhere for the liquids to go. Now, if you modernize your system, you get more water, some running water, then you have a flow rate issue, right? Because chances are you're not going to be able to seep the water fast enough with just your pit. So here's an example of what your design can start looking like with a pour flush latrine or bathroom of some sort. And just to talk briefly about the latrine setup in general, there's an advantage we see right here. If we can have a pour flush system where you take a bucket of water and you can flush it through. I mean, you could have running water too in the whole toilet deal, but essentially even with a toilet, if you didn't know this, you could take a bucket of water and pour it into the toilet bowl and it will flush the toilet, right? That's just what's essentially happening with the mechanics there. So if you flush it, then you get your waste, and then you can, given some slant to your piping, you can then have your actual pit somewhere that's not directly underneath where you're sitting or standing, right? So the nice benefit there is you no longer have concerns about people falling in. That's a legitimate, important concern that we certainly want to avoid, right? That also means you could potentially keep your latrine structure in place and dig another pit and pipe a new pipe to a new pit without changing everything, right? So there's a couple advantages there. This is also the technique we would essentially use if we're doing a septic tank system where this might be the septic tank. Usually we'd make the dimensions a little different and then have a discharge into a field or into a seep field. So that's kind of an overview. And if we think back on what made latrines themselves good or bad, or the pros and cons there, a lot of those pros and cons, the odor, the flies, things like that, are actually solved if you can keep a little bit of liquid right in what's it's called the P-trap. Don't think that's urine meaning. I think it's PEA. But there's a bit of liquid that will stay right in this S curve in your piping that will prevent odors from coming up back from the sewer line up through your toilet. So if you ever notice, the toilet bowl has some water in it, right? That's going to prevent any foul odors coming from the sewer lines that you're discharging your waste to into the bathroom, which is very nice to have that in place. It's also going to prevent insects from being able to travel to in this case, the latrine, the waste, and out. So just that ability by itself sounds like a pretty trivial thing, is actually good for both the hygiene aspects with the flies and all that, and simply the aesthetics, right? It really is a big improvement. So if we can do that, that's great. And then kind of the question is, well, how much volume are we going with? Okay, so just to, another example here, you could have a toilet that doesn't even have the toilet backing. If you're just doing a bucket type style, that's possible. Or maybe you do have piped water and then you'd fill that. Regardless, whatever the case you're using, you see again here that curve in the piping. That's going to keep some standing water there that will be flushed every time you flush it. And this is also the schematic showing that option to potentially divert to a new pit. And in this case, they're showing 2 leach pits, and you can kind of see there's perforations here on purpose. So the hole itself stays pretty solid, but the liquid can seep into the soil. And in this case, perhaps your soil doesn't seep very fast, so maybe you would do 2 and fill 1 and then divert to the other. That's probably not too common. Maybe this is simply filling with solids eventually, and then you can transfer. That's kind of what I mentioned, right? But perhaps you would have some design on purpose that way ahead of time. Okay, so thinking about what else we can do. I guess I didn't mention this last time, so I've got it back here before we really dive into the septic. With septic fields, we'll see we generally don't want vegetation over the field, or at least not vegetation that will grow deep roots. So something like grass would be good, something like a tree would be bad. But one thing we could do, we mentioned this covering latrines, but if we're doing different pit latrines and moving the latrine or moving the pits, we could do what we might call an arbor lieu, where you plant a tree on top of your old septic sludge, right? And then that tree will grow quite happy. Perhaps if you're growing something like some sort of a nut tree or something, maybe that's completely fine and safe to eat. I think there's maybe some questions there about fruits, may or may not be the right idea. But regardless, you'll have a happily growing tree, and that should stabilize that material and help keep it all mostly intact as it's converted to just soil and assimilated into the natural environment there. Should also help prevent any erosion or something from starting to wash out all this potential contaminant, things like that. So there's a few advantages. Kind of keep it secured and separated and intact. Give it a long time to sit there. Okay, so that's another possible composting style we could do. Okay, so septic systems then, we'll talk kind of at scale of what we would typically do in the US, and we'll also think along the way, how could we get close to this for scenarios where maybe we don't have as much infrastructure, design, education capabilities. So a typical home would be equipped with a septic tank. Many times the septic tank itself would either be 2 tanks or more likely a tank with a couple of chambers. It's not strictly required, but essentially this tank will be an anaerobic digester. So we are going to rely on anaerobic processes. And these will essentially help us to digest the sludge that's formed there. So we'll have a lot of bacteria growing. It's not aerated, so it's not they're not growing with oxygen and doing respiration directly. They're going to take things like sulfate and grab the oxygen off of that to use as the oxidizer, convert materials into energy. So the biological processes will look a little bit different, and you'll end up with reduced compounds largely in that effluent. So this will be, that does do a decent job of degrading solid materials into dissolved materials. It won't be perfect, and it'll depend a little bit on what kind of materials are going into the toilets. You know, in the States, we typically flush our toilet paper. In Nicaragua, they don't typically flush the toilet paper because the plumbing's not big enough to handle that. It'll clog the plumbing. So depending on what kinds of solids you're adding there, you know, toilet paper is, for the most part, soluble and will disintegrate pretty well, but it could leave some residual. Or perhaps there's something else that's just people are adding. Maybe it's a diet that people are eating. There's some variation, could change the conditions, the speed at which the solids will build up. So the septic tank itself is here then for digesting those solids, trying to reduce the amount of solid particles. And importantly, the other thing that this tank is doing is preventing those solids from leaving into the field. Because if we have solid particles going into the field, eventually all the pores of this field and the soil and everything will get clogged up, because these will be pretty fine particles. So what we're designing our system for really is a way to get rid of the liquid waste in a way that's avoiding human exposure and is sustainable over a long time. So what we need then is to reduce the amount of solids and then prevent the solids from going anywhere. That's kind of the whole scheme of a septic system in a technically speaking. So this anaerobic processes then, these will reduce or digest, I'll say reduce solids buildup. And then it will also act as a sedimentation chamber. So when we flush the toilet, water goes into this chamber. There will be some flow rate there where the water is discharged, but it's going to end up slowing down and having a lot of residence time in the septic tank, and we'll design it accordingly to have typically a day and a half to 2 days of residence time before the water leaves. And it'll typically also pass under a baffle, and then we'll have some sort of a screen probably before the water enters the exit pipe. So with all of that, we ideally have removed solids from the effluent that's going out. And the reason we care a lot about that, and I'm going to write this as let's say sedimentation chamber. One of the primary reasons we care about that is establishing a leach field is generally pretty expensive. It takes oftentimes a lot of land, and you're going to have to put in a lot of pipes. You're going to have to dig a lot of this field. You have to dig it to a certain depth to make sure everything is proper in terms of your water levels and where the stuff can go. And then in addition to that, you also have to line the pit with gravel or line the field with gravel, probably put some sand, maybe put some geotextile over it to prevent soil from above to clog it up with smaller particles. There's a fair bit of labor and materials that go into just getting the field in place properly. So once you have the field in place properly, it's really important to keep that in place and happy and functioning well. Because if that gets clogged, you either have to just dig it up, clear all that dirt out, gross, and put in new stuff, or make a new field somewhere else. And that's just, you can imagine those expenses will add up quite a bit. Now, in Nicaragua, what they typically do is actually quite simple in the areas where they have soil that drains really well. Instead of doing a leach field, and this is just a sort of a two-dimensional look at it, this probably looks like if we were to take 3 dimensions, oftentimes you have kind of a network of pipes, something like that, all discharging simultaneously into a wide surface area. In Nicaragua, they typically, a lot of places, they have really good, well percolating soil. Water drains really quick. They don't need a lot of area for it, and so they just do kind of one pipe and a little bit of space around it with gravel and stuff, and they call that good. And given that they don't have huge flow rates, they don't have washing machines and dishwashers and things like that, that generally is sufficient to handle it. So if they did have a problem in that case, maybe it's not a huge deal to dig another trench and put in a new pipe. It's still something we want to avoid, but in that particular case, they might feel their priorities are a bit different. Okay, so then the other aspects of this, what we're relying on the soil to do for us, in addition to taking the moisture, the water, we're also relying on that soil to do some kind of natural filtration, some granular filtration essentially, over some distance, and we regulate how close our septic tank can be to the nearest water supply, right? So theoretically, unfortunately, this septic discharge is going to make it into a water supply, possibly. Ideally, you have a deep well that's, maybe in some confined aquifer. Sorry to bring up, bad exam and all that, but hopefully you have some protection from there. And if not, we'll make sure there's some distance, that there's enough distance so that filtration can kind of happen. And so we have specific benchmarks. I think 100 meters is typical. And that would be sort of a radius, I think. Okay, so there's a few design pieces for that as well. Okay, what would it typically look like in one of these reactors? Well, we'd have some influent, and here we, have our septic, or our wastewater from the house discharging into here. This would be approximately, this is probably a 4.5 inch pipe. So here, this one's saying this might be cast iron. We also use PVC, the drain waste vent caliber for this type of wastewater in homes, and it's called 4 inch, but I think it's 4.5 technically. Okay, so that would come in. You'd probably have the flow go downward here, and so then you're essentially just preventing the flow from trying to go straight across, right? That would be not so ideal. So from here, it's going to end up mixing, all throughout the system, and ideally, it's not going to be a fast flow, and so you're going to have, or compared to the reactor, right? So you're going to have a residence time, so hydraulic residence time. And I probably have the details written later, but just making a note of it. Something like, 36 hours or so. In order to give the particles time to settle before the liquid discharges out the other side. And you'll see oftentimes you'll have a discharge pipe that will require the water to be flowing upwards. So you still have a little bit of potential there for sedimentation to be kind of going against that. Probably some sort of a screen here in case there was some sort of particle that could make it through. We also don't want to collect from the very top here because we'd probably get some sort of floating scum. So our particles will either float in some cases, some bubbles or whatever, or sink, right? And there's a decent chance there's some methane production in here or other gases. And so we'll probably have some sort of vent that away from the area, let those gases escape without, risking some sort of explosion or anything like that. And then we'll collect our water from below that scum layer on the top. Okay, so in these tanks then, you see at the bottom we have sludge that's accumulating over time. This is the stuff, eventually this will shrink our effective volume and cause us to have a situation where our residence time is decreasing because there's less volume. And if we call this hydraulic residence time theta, we say that's the volume over flow rate. So if we have less volume, then our residence time shrinks, right? So there's a couple things to consider here. If your residence time shrinks too much, then maybe your particles are escaping, right? So even if your water is still flowing fine and you had a bunch of sludge accumulation that was too much for your design, you might be clogging your septic field even before you have a direct backup that this, if the sludge increased too much, maybe your water just couldn't go anywhere, right? That would back your system up. But so this is kind of the technical reason why we aim to have a sludge pump out every so often. And the typical recommendations, I think, is something like 2 to 5 years or by inspection. There are maybe some ways to add some chemical or even a microbial agent or aid to enhance the sludge degradation, so you wouldn't even have to pump it, perhaps. I've heard some things about that. I don't have firm knowledge if that's always an option or sometimes an option, or to what extent it works. You could also stir the sludge, and that would help promote the digestion, but that's not very practical and would also kick up your solids, and you wouldn't want to do that either. So there's some ways you could potentially deal with it, but typically if you could just pump it out every so often, that would work. In the case where maybe you don't have access to pump trucks, so again, thinking of a developing context here, perhaps you just over-design the pit itself to make it very large and hope then you could use it for 20 plus years without an issue, right? Just extend that lifetime a lot further by over-engineering in terms of the volume of sludge that you could handle, maybe one of the more practical solutions. Still ultimately could end up with an issue, but hopefully doing that way would at least allow that the homeowners, the families, whoever, to have plenty of time to be ready for that, and to have that time to develop their own capacity further. Okay, so a few design standards, and this is from this pamphlet. I just posted this morning to our Moodle page. This was a pamphlet we kind of designed. We took this from several different sources. I'll show you those at the end of these slides. But essentially, we can take typical guidelines in the States, and we'll take a look at those now, and then think about, okay, what all might we need to adapt in resource scarce settings. Okay, so a few guidelines for septic tank usage. How many of you, by the way, have a septic tank system at home, or your family grew up with one? Anybody? Don't? Maybe? A couple? And now, are those the aerated types? So a lot of them in Louisiana have an aerator. It's still an on-site system, but it's going to discharge to a ditch somewhere instead of to the ground. Okay, so probably that way. Okay, so I'll probably talk more about that after, so probably next time. I'm going to put some slides together to that. Those are, since they're aerated, they're aerobic. So it's actually quite a different scenario in some ways. You're still going to try to have particulate removal and things like that. But most places where we have an on-site system, if we can get away with it, we don't do the aeration, we discharge to the ground. So those are a little bit special case scenario. When I was growing up and I was young, I know my family had a septic tank system, and I have a lot of siblings, and it was a small house, so I think at some point we had to upgrade. We had some sort of issues, I remember. We were over capacity for that system. So for these aerated systems, the guidelines will probably be kind of similar, I think. For septic systems, again, I'm going to make a slight distinction there. Septic meaning anaerobic to the soil, and an aerated treatment unit being like that on-site with the aerator and discharging to the surface. So for the septic, there are a few best practices in order to not clog the system, right? And so It says, do not flush materials that do not easily biodegrade or any strong chemicals. The strong chemicals could kill your microbes, and then that process of degrading, destroying the sludge itself will stop, and so you'll have sludge accumulation. You want a healthy biological population. You don't want to poison all your microbes. So you wouldn't want to flush a full can of bleach down the toilet, right? Non-biodegradable stuff, so you might think maybe coffee grounds is probably not the ideal thing to flush down into a septic system, and both of those would be true for ATU systems as well. You don't want it clogged. You don't want it, particles that are just going to fill up the system and sit there. In general, that's probably a good idea for municipal sewer collection systems too. The chemicals will, you shouldn't do anything that's like super hazardous, but a can of bleach will be diluted enough by the time it matters for wastewater treatment that wouldn't cause problems in a sewer system. Okay, so then says, so another guideline here is to plant grass or other shallow-rooted plants over the absorption field. So again, here's the picture, right? We have a home, we have the septic tank, and then the absorption or leach field here. So the recommendation is to plant some plants there, but make sure they're shallow-rooted, right? And for those of you that were on the trip with us in Nicaragua, we found a lot of situations where we were, and I'll grab a couple pictures for this one. We found a lot of situations where we were trying to dig a test pit, a percolation test. So we were going to do a percolation test in a particular spot, and then we had to look around and say, oh, are there trees around here? What's nearby? Are there going to be a lot of roots? Where is this septic tank and leach field going to be? And sometimes that was a bit of a challenge, right? Sometimes we didn't exactly know. Oops, yeah. I'm just going to scan through a few and find one. And if we didn't have a good spot, what do we do, right? It's like there's some question about, should we suggest that they cut down a tree? Probably not, right? So on their property, where can we do this? And that was a pretty big question. So here's the first one I found here. We made the pit here. You can see there's a tree right behind Caleb there, and I don't think there was too many roots in this one, but we might be able to send the leach field one direction, but we really shouldn't try to put this under this tree unless we're planning to remove the tree entirely, right? So there becomes lots of questions like that. Like, okay, what are we doing? How are we going to design that accordingly? And then what are we going to plant on top to keep the soil there and keep everything happy? Okay, so then another, trees and long-rooted plants should be kept away from the absorption field. And when we say kept away, that also means like it really should be a bit separate, because the roots, when they start sensing some good nutrients and some like nice water, like continuous water, even in the dry season, they're going to want to go towards that septic leach field. And those roots will find their ways straight into the pores that is where the water's coming from, right? And so they will literally just go and find their way into those exact pores that you're trying to keep free. So it's quite important to do that. Of course, the tree will be happy, but the septic tank will not, or the leach field. Okay, so as we think about how to design a septic tank, so there's two aspects really: the tank itself and then the field, and each require a bit of design. And we'll take a look at the tank. We mentioned already the functions, right? We're trying to get solids digestion, but perhaps more importantly, solids separation, right? The digestion aspect, we assume that will go on, and we have to consider that to an extent, but eventually we'll just pump it out. So with that in mind, we have to design it large enough to handle a sludge accumulation rate that means we don't have to pump it out every year, right? Ideally, it could wait 5 years or so. Even more ideally, perhaps we, in a developing context, we just make it so large that it's not going to be needed for 20 years or so, or maybe ever, perhaps. Okay, so then here's the scheme, right? We have the influent, we have an effluent, probably have some access port or lid. We asked about that in Nicaragua, and they don't have a specific port that you can access from the surface, but if you dig to it, there are concrete panels that you could remove a panel and access it that way. Okay, so then if we have some number of people in the household, and these are, again, based on typical water usage, I think this is in the United States, at about 45 gallons per person per day is the metric here. So if you have a household, or maybe it's 2 households, or maybe it's like a shared space, you could just think about how many people are using this facility. And in some scenarios, maybe you build a modernized bathroom that's serving 3 households on a corner. That's something that you could potentially do, right? I think in our scenario in Nicaragua, they were doing 1 per household, but sometimes 2 families might live, or a family with their grandparents and so on in 1 household. So you might have some large variation in the size. So given some number of people or some flow rate, right, you would size the tank accordingly for a 10-year lifespan. Okay, so this is our typical design scheme in the US. It would be at minimum 135 gallons. So if you think about like a 55-gallon drum, how big that would be, a little more than twice that in terms of volume. That's actually not too big of a tank that you'd have to dig as a pit, all the way up to nearly 1,000-gallon size. And I think, if I'm not mistaken, the Amigo's typical install is somewhere between a cubic meter and 1.5. It ends up being, I think, over this mark. So it is quite large. But it's not very sophisticated. It is just a ditch or just a pit typically, influent, outfluent, no baffle or anything like that. Okay, so that's that design then, for that 10-year design, is aimed at, after 10 years of sludge accumulation, we are still getting adequate residence time for particle removal by a sedimentation during this, during typical use, right? So at some point, you still have to get your particles to settle, even with all that sludge, right? Even though the water is going to be staying in there a shorter amount of time. Okay, so that's on the tank design side. On the septic field side, we could use what we might call a percolation chart and do a percolation test to see how quickly water is flowing through the sand or the soil, whatever material we have in place. How quickly is it discharging? And what we're after here is it's basically a flux, right? So we're looking for some amount of water over time. So if we think about digging one of these percolation test pits, where we have some pit like that where we were digging 1.5 feet depth and 1 foot diameter, or kind of maybe a square. Essentially, we'd fill that with water, let it saturate the soil, fill it again, and measure how long it takes before for the water to drain downward, right? And we check over time. So what we're looking at is some change in depth or distance over time, and we can kind of relate that to, we've got some surface area here in this pit, and water is discharging throughout that surface area. And so essentially what we're getting by looking at this is kind of a flow rate, Q. This is a dimension of distance cubed over time. And we're dividing that by area, which is, of course, some dimension of distance squared, right? So if we take flow rate divided by area, that's giving us a flux, So when we did the percolation test, essentially we're measuring the flux of water in this pit, which is why we designed it with some pretty standard size, approximately standard. And what we're resulting then in is a flux of water into this media. We can then estimate, okay, this kind of soil is giving us this amount of percolation, right? So very, very simple version of all your groundwater and all that, right? You probably wish you could just dig a pit and pour some water in, right? And there's your test. Okay. So thankfully somebody else, can do all this math for us, figure that out. That's up to all you now that you know that stuff. So we'll get some sort of infiltration rate, and we can measure this in, let's say, inches per hour or per minute or something like that. So here we've got some infiltration rate, and I think it says somewhere, but this should probably be, let's see, this might be inches per day or centimeters. Yeah, there's a small oversight. I think it's probably listed somewhere within the pamphlet. But this will be some distance per time. And so if we measure and it's, I'm just going to say distance. Maybe this is centimeters. I think that's seeming a little fast per hour. Okay, regardless, if we have something that's happening, the infiltration rate is pretty low, then we have to say that then we apply some ratio for our septic field area. So if normally our default design is we have some number of square feet required to percolate all this water, in a normal circumstance, normal here, maybe it's 10 square feet per gallon. In fact, actually this is already in here. So this 46 to 60 range, that's corresponding to, you need 1 square foot per gallon per day. Okay, so if you had 100 gallons per day, you need 100 square feet under this circumstance. So that was already built into the thing there. So if you look, when we have a slow percolation rate, I think we must divide by that 0.4. Essentially, we're gonna, if it's slow, we need more surface area. That's the point. And we could do that all out with the math accordingly. And so we can design our system based on, here's our infiltration rate. Then we're gonna multiply how much area we need accordingly because it's just taking us slower. Now, what you'll see here is this is pretty, heuristic in the sense of we're going to find something that works and go with that range within that range that works. This is not exact science to say exactly 32.3 extra square feet this time, right? This is going to say to whoever's building this thing, okay, yeah, we checked the soil, it's got this factor, so we're going to do 2 times the amount of field as normal, and we should be all right. So we'll get a kind of a ballpark number and make sure that can be situated. Now, one of the challenges we were having in Nicaragua is that the team that goes and installs these septic systems, they have a lot of reason to want to do everything exactly the same for every person, every household. In fact, one of the solutions for the cases where the septic really was not a good solution was to do something a lot like adding a diversion system here, except this was just to divert the gray water. So they would have their toilet flushes still go into the place, but there was too much volume if we were taking shower water and other wash water that during the rainy season, the thing would flood, right? Or situations like that. So unfortunately, we'd have to just divert the gray water to run off to the surface. That's not great, but that's already happening. So it's at least it's not worse than what was there. And the fact that they do have the flushing toilet is better than what was there, right? So it's not the ideal situation, but it's still an improvement. But the thing was, there's a social aspect. Some families got that, and it was probably a $5 or $10 part to install it, something not too expensive. And some families were like, why are they getting it and we don't? Now they're living on the top of a hill with no drainage issues, but they want that because, you know, it's some protection, it's something extra. So there's actually some within the communities, some real tension that, like, oh, now we can't adapt specifically for a scenario because the communities that they're working with, you know, we're feeling like, hey, I paid into this and they're getting extra. Like, what's the deal, right? So there's some tension there in the social aspects that is another hurdle to taking a very specified design, right? And so that's not something we would necessarily think about in the States. We would say, oh, okay, yeah, we're gonna design a home this size. It'll be able to handle this number of people and stuff. So we need to do X, Y, Z. We have a different problem. In developed countries, a case example was Dr. Lesage. Geoffroy Lesage was with us. He joined us as a professor from France. And he was talking about he upgraded his house recently, or is in process, just adding a kind of an extra room to it. Took what used to be sort of a patio area and enclosed it and increased the size of his house a little bit. Well, he has a septic system, and now because of the square footage or the number of rooms or whatever, now the French policy is, oh, you have to upgrade your septic system and field accordingly because now you could house this number of people. Of course, he didn't change the size of his actual household in terms of people or the flow rates, but there's that distinction that says, oh, now you must. And so, you know, there's some the pros and cons, I guess, either way. But so now he's going to have to spend quite a bit of money to update that before he ever is able to sell the house. I think he's fine to continue using it at the moment, but it's a pretty sizable cost. Okay, so all that to say, we can design very specifically, but there are some challenges to doing a specific engineering design per household if we're doing kind of a community development project, right? And this is an active challenge for them. One of the communities we went to, maybe I'll find some photos here. Mayokunda was the name of the community, and they have their soil was so variable from one household to the next that it was simply like you'd have clay here, and we had bedrock over here, and one spot that was percolating great, and that group finished like in 20 minutes. They're like, we're good, okay, let's hang out. So it was very interesting that there was such variability there. Let's see if I can get at least one of these photos. Yeah, so speaking of Geoffroy. So this one ended up being quite muddy, and this is the one that sort of collapsed in on itself. When we went to check it, that was not very useful in terms of the actual design. Let's see if I can find another. Okay. All right, so just to follow this kind of instruction manual a little bit further, here's the percolation test kind of concept. Ideally, what you would do this in exactly the conditions you're using, perhaps even having added some gravel. That's certainly not something that we were capable of, so we just went straight into the soil where we were planting it. Because what you want to model is what's going on in the place where you're going to do it. So to do it, it's basically dig a ditch. This instruction is saying 6 to 12 inches. We were doing 18. Kind of depends on what's going on. You probably don't need to do too much more than that. You just want to get to the soil that the field is actually going to be in, right? In case there's some top layer that doesn't, that's a little different than what's underneath. You'd want to get past that So you get some sort of ruler or stick to measure over time and test that. Okay, so you let it fill, let it saturate, and then you start again later, filling once more. Okay, so example provided here, if you take 75 minutes to go 6 inches, and that's what I was getting backwards over here actually. I think this infiltration rate was inverted, so this must be minutes per inch. Feels a little backwards, especially after I talked about the the flux here, but we can do 1 over flux and that's fine too. So minutes per inch, if it takes that, and which also explains why I was confused about the ratio, right? So if it's only takes 30 minutes or less to go down 1 inch, you don't need a whole lot of septic field. That was the point. Okay. So you can get some value here and then find your situation accordingly. And then we have an equation saying that, okay, the area needed is going to be the flow rate times this area ratio. And so if we skip back and we say we have some flow rate, can multiply it. If we had 100 gallons per day, we multiply that by this 0.4. That means we need 40 square feet of drainage area to accommodate that. Okay, whereas if it was very slow percolating, then instead of 100, then we need 200. Okay, so it goes from 40 square feet to 200 square feet, depending on how well your area percolates for 100 gallons per day. So you can kind of see that's, that can make a big impact. And for developing context, you don't necessarily have 200 square feet or the, infrastructure and all of that to put that into place affordably. Okay. Another thing to kind of consider is geology in general. We have a map. There are not very many geological surveys for Nicaragua. We don't have a ton of data there, but I was able to find this one, or might have been the class that found it. And so in the region, we can kind of see some areas that are looking pretty good in terms of, and this is kind of a description of soil workability. So probably correlates to soil percolation, but not necessarily. This could be some other aspects. Let me say workability. This is probably more so for farming. And I'm going to put a question mark here because that's kind of an assumption I'm making. But it could be useful for amigos down there and for anybody else that might, you might look at a map like this to say, okay, so how much of Nicaragua could actually use septic systems as a tool to provide sanitation, right? Maybe that's your question. And you'll notice that a lot of places are pretty good. This corridor right here seems to be a bit of a problem. And if we were to look at where we were working, so Chinandega proper is right around here. And we went to some communities out in this area, but we also went to Mayacunda, which is more like this area, and I should probably use a different color here. And so certainly it does kind of seem like it's correlating pretty well. So if this is Chinandega, there's a fair amount of communities that are in good areas, but then some, as we head towards Honduras a bit, more difficult ones. By the way, that second volcano, with the crater lake, that is located right about here. So that's why we were seeing the ocean in two directions, right? We saw ocean out this way as we climbed up, and then we looked kind of across the crater from our vantage point, and we could also look out and see, if you remember seeing that there's like a shipping vessel out there that looked like it was just floating on the horizon, right? Because we could kind of see that on the water. And then vaguely, it was pretty hazy, but you could still see some mountains over here and over here. So that would be mostly seeing Honduras and a little bit of El Salvador. So that's just a little picture of what we were seeing there. Okay, so this could be useful, and we could kind of have some understanding, even before we even go somewhere and try to think about what can we do, is this an option? Should we even consider septic systems at all? And ideally we may have some better tool, but this would be at least a starting point to think about. Okay, so what kind of outcomes can we expect from septic treatment? Well, we do, even just simply in the septic tank, typically have some pathogen removal. So we might get 20 to 75% reduction in pathogen load. That's nice, but it's really the soil's action over some length of distance that's really going to be what's providing the removal and safety for that. We should get that removal of settleable solids. Like I said, that's really to protect the drainage system, and that should be pretty stable, assuming we're not doing anything that's disrupting the system, right? We also probably ought to inspect every so often. Now, in the cases in Nicaragua where they've put these in, I don't think they're going to be doing any inspections. Maybe they'll do an inspection of their oldest systems at some point to check on it, and then they would probably use that one or a few that they check and say, okay, if these are our oldest systems that we've installed, here are the dimensions, we're looking good, or oh look, we probably should have pumped out a year ago, whatever the result is, that might inform them on what to do with the other pieces. But for the moment, they don't have any immediate plans, and I don't think they have any immediate needs. I don't think they've had any backups outside of high water table issues or just simply clay soils. Okay, conversion of biological oxygen demand to methane and CO2. So that's going to be one component there. Those anaerobic processes will be doing. Generally, you can handle a wide range of organics. So even if you do flush some cooking oils, the microbes might be different microbes, but there should be some microbes that'll be able to handle that. You wouldn't want to do a ton of that, probably, but they can handle a wide range. When you do have anaerobic systems, you generally produce less sludge. So if we think back on the aerated systems, we actually expect a little faster sludge accumulation. So those probably need to be pumped out a little more regularly of the solids in there. So those are sort of the treatment outcomes we expect of a typical septic systems. Okay, so a few things that we try to keep in mind that could clog or kill the system. Again, we don't want to kill off all the bacteria. That causes a lot of problems. pH, if we were to add a bunch of acid or base, maybe we were doing some drain cleaner stuff and didn't really think about it and added a whole bunch of sulfuric acid, which does a pretty good job munching on organics like clogs of hair or something. But that could also probably kill a lot of microbes, right? Especially if you shock your system with a very acidic condition. So that's certainly something that could happen and would not be so good for your organisms. Temperature shocks potentially. I actually don't know how they manage temperature for septic systems where the ground freezes. I probably should know, but I don't. I know that their wastewater lagoon systems are quite interesting sometimes because their wastewater will literally just freeze in place and then be sitting there over winter, and then when it starts warming up, they have permits that adjust accordingly, seasonally in terms of their discharge rates, because they'll have some accumulation during winter, so it's going to accumulate in the pond, and then as it thaws, they have to do some special precautions and make sure that it gets enough treatment, and they have a permit to discharge more, and then back to a lower level, and then none during the winter, right? So it's very interesting. Okay, mixing could be important. Like I said, if we did mix, we would potentially get a lot of particles stirred up, so we don't want to mix. There have been a few research studies where maybe you have one chamber that's collecting most of the solids and you do mix that occasionally, and then a second chamber for the sedimentation to kind of protect it. And you can, if you do all that, you can get a slower buildup of solids because it's doing a better job digesting them and all that. But at the end of the day, that's not very practical, and typically we would just not have very much mixing, and that's probably for the best. Okay, so retention time was the other major factor for considering whether or not you're going to clog your leach field, because those particles need to sediment. So if you fill your tank with particles or with sludge, particles, that residence time is like a few minutes and just goes straight out. You're not sedimenting your particles. You're going to clog your leach field. Okay, so a few other considerations for design. Since you're anaerobic, you're typically going to have some hydrogen sulfide, and that's pretty caustic. So you can't use a metal chamber. You need to use concrete, typically. Talked about it a lot already, that sludge accumulation rate. It's very important. So if we can estimate that or get some handle on that, that would be good. And lastly, that ideally you protect your drain field at all costs. This aspect is different for Nicaragua, I think. I think the actual septic tank is probably more expensive than what they do for their field, because they typically just run one pipe if the soil is so good. But this is a typical consideration, typical priority. Okay, just real quickly about the actual biological processes. I'm not the microbiologist expert biochemist, so I'll defer to Dr. Mo or Bivens or somebody else to give you the full details and test you on all that. But you probably recognize when you have organic matter, the process in which we're degrading it is going to depend on the conditions, right? Also depend on what kind of microbes are there, and that also depends on the conditions. So if we have some sort of organic polymers, that's a generic term that could mean DNA, that could mean lipids, membranes, all sorts of stuff, organic stuff. Those will typically, this will be going through some sort of a hydrolysis process through fermentation, kind of splitting off pieces, breaking them down a bit. You'll get from there a lot of alcohols, carboxylic acids, things like that. And we see that would be about 75%. A little bit would just go straight to hydrogen or CO2 from that. And about 20% would probably go to acetate, which would play a different role here. Then you have acetogenesis, where you're producing more of that. You'll get about, from these kind of short chain carbon molecules, you've got some production directly of CO2 and hydrogen, and about half of it going to acetate. So from there, you have methanogenesis, where you'll form CO2 and methane from each of these pieces from there. So kind of a very, very broad brushstrokes demonstration of where we're getting to methane and CO2 in this type of process. You'll see we also have hydrogen gas potentially. That's probably going to be consumed in the processes there, but methane and hydrogen gas are both explosive. So one thing to think about as well, we just do need to make sure that we are venting our system here, right? We're not accumulating explosive gases in our in our tank. Okay, so that's pretty typical. If we were to look at aerobic treatment, of course, this is going to look very different. We have different biochemical pathways, different products, mostly CO2, right? Consumption of oxygen, production of CO2, and instead of anything like H2 or H2S, so hydrogen sulfide, anything like that, we would get oxidized compounds like sulfate. We'd be driving, this probably also produces a fair amount of ammonia, and an oxidizing an aerobic system would probably be converting that ammonia to nitrate, for example. Possibly, maybe we'll have some denitrifiers get to N2, but we'd expect, the resulting compounds to look a lot different based on which way we're going. Okay, just a list of a few advantages here. Kind of been talking about them already. The lower sludge amounts, removal of the settable solids, this conversion. Okay, kind of a recap there. Okay, so as we think about, one thing we haven't really talked yet about is the speed at which the solids will accumulate. How do we model that? Can we model that? what would go into that. So we could take some sort of a mass balance, and that's what we have here, in order to say, well, we have some change in mass accumulation. So if we say dm dt, that's what we want to kind of solve for. That would give us a way to predict how many years are we good to operate before we get into some sort of trouble with a residence time and things like that. So that would be useful to know. This is something theoretical that several researchers have tried. It's pretty empirical in the sense that we don't have enough exact information to do all of this by calculation. But if we did, the way it would look is kind of like this. A mass balance here where we have dm dt with a flow rate times the concentration coming in, and that would be of solids, minus the concentration going out, which hopefully is 0, right? That's hopefully 0, ideally, or at least close enough to 0 so we're not clogging the pipes. And then we would have some rate at which the mass is being degraded by just that anaerobic decomposition. So that would be this term here. And then we'd be yielding extra solids as microbes are growing. They would also decay and then be degraded. So there's a balance there. And so solids generated would be this guy. And so this y should be some sort of a yield factor or yield coefficient. And so just taking kind of a big picture look here, we should be able to find some kind of a balance where we have solids coming in, obviously, when we flush, solids being degraded by the bacteria, and some bacteria growth. So all those put together, hopefully we have close to a steady state, or more probably not steady state, but a very slow growth, right? We don't want any scenarios where this is going to go be a very high number. So we'll just say hopefully small number here with respect to how much time we're designing it for, right? So we can take a look at the flow rate, or the units here. We would say Q would be that raw sewage flow rate. That could be cubic meters per year. C naught would be the influent concentration of solids, maybe kilograms per cubic meter. CT would be the effluent concentration. K, this would be an organic matter biodegradation rate constant in per year terms. Delta mass, that's the mass decomposition, kilograms, and Y, some biological yield coefficient. So with that, we could make some estimation. More likely, we'll probably just use some observations that other people have done and say, okay, it's going to generate at about this rate given these typical practices. So this would be like if we could find that yield coefficient, measure that. If we could know the actual flow rate and the actual concentration. But I don't know about you, but I don't think there's many people that are aiming to measure the concentration of solids in their flushes, right? That's not a typical thing to get that level of precision of information, right? There's a few pieces of common human dignity at stake there to take those sort of measurements. Okay, so clogging prevention. Talked about it already, but that hydraulic retention time is key. And this is going to be calculated based on, and this is something I didn't really mention, is between the sludge and the scum layer. So if we have a tank with our influent and effluent, we're going to have sludge accumulation, but we're also going to have, and I did mention a scum layer, but the scum layer could grow, to some extent. So we would also have some scum layer up here. And so our effective clear volume would be between those two, right? So then we have some volume here of clear space. that's where the sedimentation would be occurring, essentially. So we need to calculate our theta accordingly, and typically we set aside 2/3 of the tank volume for just that sludge and scum. Like if we design it so that it can operate properly with just 1/3 of the tank volume, then we're good, and that generally gives us that 2 to 5 years or so condition. Okay, so then ultimately what we're saying then is 1/3 of the volume must provide a hydraulic retention time of 12 to 24 hours. So I wrote earlier maybe 36, maybe that's for a new tank. So 12 to 24 hours should be sufficient in order to provide the appropriate sedimentation. Okay, so we were talking about that sludge accumulation. Well, there have been some theoretical attempts. That's what we just looked at, mass balance approach. But typically we're just going to use, like I said, some sort of known empirical, people have seen, oh, it typically requires 5 years for a family of 3 or something, whatever the case. So we would say the volume of sludge, we could relate it in a couple different ways. We've got an exponential here. 47 times how many years raised to the 0.675. Very arbitrary, right? That's not coming directly from a mass balance. That's just people notice that having pumped out every so often. Or a volume of sludge equal to 13.39 times the number of years plus 50. And this is volume in gallons of sludge per person. So a couple different ways to do it. Both of these yield a pretty good standard number, and the literature on it reports about 95% confidence. So it's not too bad, and definitely better than trying to quantify the amount of solids that we're flushing in the toilet, right? Which, also could vary if one of the people in the home is an infant, right? Maybe there's not too many solids, mostly going into diapers, right? There's a lot of variables there that could complicate things. Okay, so just to wrap up here, there's basically 3 places I can point you to if you want some more information about these in particular. One would be EPA's guidance for homeowners, and I think this is a pamphlet PDF. So there's a little document here, goes through some stuff. You'll see it's kind of designed to print and fold, so it's upside down for part of it. Bit of information there you could take a look at. There's a book that is available through our library system, Biological Treatment Processes. Took some information from there. You should have access to that if you wanted to. So there's some good info there. And then one paper that was reporting on this sludge accumulation and the mixing, I think, in septic tanks, right? Effective hydraulic mixing. So if you were curious, there's a few good resources there available here. And I also put the pamphlet that I took some of those slides from on Moodle. Okay, that's about all I have. You guys got any questions? Okay, well, I'm planning to make some new slides for the aerobic types. It's not as applicable to kind of developing context because we wouldn't normally want to spend that much infrastructure and energy on it, but I'm at least going to put a few slides together to kind of show you that's potential alternative, and maybe for scenarios where we do get more infrastructure, or maybe make a community scale treatment system, something like that could be applicable. All right, well, have a good Easter, and we'll see you on Tuesday.